The things that go bump in the cosmic night. You're listening to Are We There Yet? The radio show exploring space exploration. Hi, I'm Brendan Byrne. 'Tis the season of spookiness, and our universe is dark, scary, and full of chilling cosmic phenomena. From cannibal stars that eat each other to our own moon slowly drifting farther and farther away, space is not without its own frights. We'll speak with UCF's Josh Caldwell and co-host of the Walkabout the Galaxy podcast about these terrifying things in space. Then, did you know that black holes have heartbeats? Some supermassive black holes have signals that mimic the thumping of a human heart. Can you hear the thump-thump of a black hole? We'll speak with UCF's Stephen Eikenberry about black holes and their strange habits. That's ahead on Are We There Yet? On this spooky Halloween episode. While there's much beauty in our universe, there's plenty of spooky and unnerving phenomena, too. In our solar system, not only is our moon slowly drifting away, but our own sun could one day expand beyond our own orbit, becoming a red giant as it enters its final stages of life. Plus, stars are eating each other. Another star could enter our universe, kicking up a bunch of comets, leading to the end of our planet. Here to talk more about the horrifying things that could happen in our universe in a million or billion years from now is University of Central Florida's Josh Caldwell. He's a Pegasus professor and associate dean at the university's College of Sciences. He's also the co-host of the Walkabout the Galaxy podcast. Josh, welcome back to the show.
Great to be here. Thanks, Brendan.
Josh, we had you on last Halloween to talk about spooky things. There's some more spooky things, of course, happening in the cosmos, right? It never stops.
It doesn't stop. Certainly not in a year. Things aren't going to change dramatically
things
from
didn't
one
get
year.
any better. So
Right, yeah.
One of the first things I want to chat with you about, and this is something that we've talked about in the past, the moon is moving away from us. And for some reason, that shakes my core.
Strikes fear in your heart.
It does strike fear in my heart. Is that actually true?
The moon is, in fact, moving away from us, yes. It is not something to be worried about.
Okay.
In fact, I frequently comment that I wish it were moving away a little bit faster because as the moon moves away from us, it's taking some of our angular momentum, some of our spin, which is causing the Earth's rotation to slow down, which means the day gets a little bit longer. And I would sure love an extra hour.
Okay, so we want the moon to go farther away.
So as it drifts out, our day is gradually getting longer, but that 25th hour, I don't know if I'm going to make it.
Is it specifically on Mondays? Because it feels like Mondays are much longer. So how quickly is the moon leaving?
Centimeters per century.
Oh, okay. So this is a real slow walk.
Yeah.
Okay. And how do we know this?
Well, we can directly measure it, in fact. And that's why I'm like, maybe it's 2.4 centimeters per year, although that seems kind of fast.
That does seem pretty fast. Yeah.
But laser ranging, so the Apollo astronauts put retroreflectors on the moon, and we've bounced laser beams off it, and we can measure the time it takes for light to get to the moon and back, and we can measure the distance to the moon very precisely. Radar also enables us to do that. And physics tells us this must happen, and we see it in other planetary systems as well. In fact, when the moon formed, it was much, much closer to the Earth. The Earth was spinning much more rapidly right after the formation of the moon, and then that initial evolution, it was moving away much more quickly than it is now.
Will it be at a point where the moon is just out of our orbit?
No.
So we'll always be
We will always
sticking
have
around.
a moon.
Okay.
Yes.
Just it's going to get smaller and smaller in the night sky.
Yes.
Okay. You and I won't see it.
It will take, we did a calculation, or I looked up for our show one time, when is the last solar eclipse going to happen? Because as the moon gets further away, it's smaller in the sky, as you pointed out, which means it's going to have a harder time fully covering the sun. So at some point, those solar eclipses will get less and less frequent because more and more of them will be annular or partial solar eclipses. But it's at least hundreds of millions of years before the last total solar eclipse.
That is really interesting because the solar eclipse phenomenon is pretty unique to the sun-moon system, right? Because of the perspective and the sizes of each.
It's kind of a remarkable coincidence that the moon and the sun have the same apparent size in our sky. We don't see that elsewhere. If you were on the moon looking at a solar eclipse, the Earth is so much bigger than the sun. It would be a very different phenomenon. You wouldn't get to see that beautiful solar corona because the Earth would be blocking out all of that, not just the disk of the sun, but all the atmosphere as well.
But we don't have to worry about that because it's hundreds and millions of years from now.
No worries there. No worries.
You said this phenomenon was spotted in other systems, right? I mean, there are dozens, if not hundreds of moons in our solar system. This happens everywhere, right?
This does. So it has to do with the tidal interaction. The process that raises ocean tides, that the moon is responsible for our ocean tides. It's that same interaction that is causing the moon to basically take a little bit of the Earth's spin energy, its angular momentum, away into its orbit and drift away. Now, an interesting case, and maybe one that would be more scary if you were moving to Mars, is one of Mars's two moons, Phobos, orbits so close to Mars that that tidal interaction means that it doesn't move away from Mars, it moves closer to Mars.
Oh, that is terrifying.
And at some point, it will crash onto the surface of Mars. And that's in the sort of tens, maybe 100 million year time frame. So blink of an eye in astronomical time frames.
For real.
Yeah.
And so just another reason to not move to Mars. So
at least maybe pay attention to your long-term investments there.
There you go. Yeah, sounds good. Something that sounds absolutely terrifying, though, that I do want to talk to you about. Cannibal stars.
Cannibal stars. Stars love to eat each other up.
I love how you said it's so matter of fact.
Yeah. Most of the stars in the galaxy and in the universe presumably are in multi-star systems. So the sun is a little bit of it's not crazy unusual for a star to be by itself, but most stars are in binary or trinary systems. So it's 2 or 3 stars orbiting each other. And very frequently, they're orbiting each other closely and interacting with each other much more strongly than the moon and the Earth are interacting with each other. And we've seen some pretty dramatic examples of this recently. So with the LIGO Gravitational Wave Observatory, we saw what are called stellar mass black holes merging and colliding and launching these gravity waves across the universe. And that's one particular end state of these stars interacting with each other. But before you get to that, when the stars, before their black hole, they're still burning nuclear fusion in their cores. As stars evolve, the sort of rate that they burn through their fuel basically depends entirely on how big they are to start with. So the bigger stars are gas guzzlers. They burn through their fuel very quickly. And once they finish doing that, they swell up and become giant stars. Our sun in 4 or 5 billion years will become a red giant. More terrifying than the moon drifting away, I have to say. And if your neighbor star was a little bit less massive, it will not have become a red giant at that same time. It'll still be merrily burning along in what we call the main sequence. And when that neighbor star, your other star in the system, swells up, it can engulf the other star in the system. You can have, if they survive, you can have one star basically pulling material off of the other if they're in a very close orbit to each other. Sometimes we'll have a system where a white dwarf, which is after one of those stars has finished its evolution, like the sun will also, after it becomes that red giant, will become a white dwarf. If that nearby star can lose material onto it, that creates nova, stellar explosions that we see across the galaxy. Stars are kind of like dogs that are always wrestling, getting on top of the other and making a little bit of commotion.
Commotion stars. This as it's eating away at another star. Like, are you visibly able to see that with telescopes? You can see the material being sucked into another star. How do you measure that?
We don't resolve photographically and see the image of that happening, although what they're doing these days with telescope technology is amazing, because there are stars that we actually, very large and relatively nearby, that we have actually resolved and can see sort of giant sunspot type structures on these stars. But what we see is, from looking at the spectra of the stars, we can learn a tremendous amount about that system. We can identify that there are 2 different stars rotating around each other. We can figure out exactly how far apart they are from each other by the changes in their spectra. We can figure out exactly how massive they are, and we can see the energy outbursts that come from a deposition of material from one star onto the other.
Very cool.
Yeah.
That's fascinating. You talked about our sun becoming a red giant. Can we go back to that and talk a bit about how I should be terrified of that?
It's an interesting thing, because when we look at other stars that are about the same size as the sun that have become red giants, they swell up to about the size of the Earth's or Mars's orbit. So the star itself...
That's huge.
That is huge, right? Right now, our orbit is 200 times bigger than the sun.
Okay.
So the sun will swell up by a few hundred times, whether it gets exactly
just a few.
to the size of to the orbit of the Earth or beyond is not known. So one might think, okay, the Earth is doomed to be incinerated in the atmosphere of the sun when it becomes
one would think
red
that,
giant.
yes.
Interestingly, there have been some recent studies that have looked at other systems, and as the star expands, it's also losing material in a strong stellar wind. It's sort of blowing material out into space, which makes the sun less massive. That means that its gravitational pull on the planets is a little bit weaker, and the speed that the Earth has orbiting the sun is greater than it needs to orbit it at that particular distance, so that its orbit could expand.
So we'll be safe.
So we could well be safe. It could be that as the sun expands and loses material over a long period of time, millions of years, the Earth's orbit would gradually expand and keep it at a safe distance. And then after it finishes that red giant phase, it'll leave a white dwarf behind, which will be much, much smaller, coincidentally about the size of the Earth itself, be the sort of leftover ember or core of the sun, and we would be presumably on some safe, distant orbit, but the Earth will be a cold and not super pleasant
it doesn't sound like
place
that'd be
at
good
that
for
period
us.
of time. Yeah,
We're talking hundreds of millions of years from now?
Billions.
Billions. Oh, perfect.
There are other things that will happen more near future if you want to be...
Hit me with it,
So,
Josh.
I mentioned that the sun is alone, and it's also relatively unusually isolated from its nearest stellar neighbors at the moment. The nearest star is about 4 light years away. That's kind of on the larger distance from what we typically see. And so we're all orbiting the Milky Way together, and we can map the stars in our neighborhood. There are about 30-some stars within 10 light years of the sun, about 100 and some within 20 light years. And they're all moving at different speeds in different directions. And in the millions of years, not the billions or even hundreds of billions of years, a star will come within our Oort cloud. And that's the distant giant reservoir of comets in our solar system, very weakly bound to the sun, and extends out to a significant fraction of a light year. So a star could pass through that Oort cloud, stir up those comets, and trigger a comet shower in the inner solar system. So by the gravitational interaction of that star with all those comets out there, some of those comets will undoubtedly fall in to the inner solar system, and we could have an increase in major impacts on the Earth. In fact, things like that have been speculated as possible explanations for some of the past giant impacts on the Earth that have led to mass extinctions. I think you and I are okay.
It's still terrifying.
In our lifetimes, I think we're okay, but definitely impacts are something to be taking seriously. They will happen again.
And it's all because another star may stir up the Oort cloud.
It doesn't even, and such disturbances may have happened a million years ago, and it'll only be, say, in 50 or 100 years from now that a comet will come in and pose a problem. So this is why people take very seriously to map, identify, track the orbits of these new objects, and we have to constantly be doing it because their orbits are always changing, new comets are always coming in, and they could pose a very, very serious threat.
Let's end on a more positive note, though.
Sure.
When it comes to that, though, it does seem like astronomers are getting much better equipment and tools to measure possible asteroids and comets, right?
There's been a real revolution, I would say, in the last 30 years or so in automated monitoring observatories that are looking specifically for small near-Earth objects that won't destroy all life on Earth, but they could be catastrophic regionally or even globally, depending on their size. And so we've made tremendous strides in identifying the population of these objects, mapping them. There are new space observatories that are being planned that will be launched this decade to map those out. And as I said, it's not something like once you've done, you check the box, say, okay, I don't need to worry about this anymore. Their orbits are always evolving. And so it has to be a constant monitoring process.
Because we want to be around to see our sun turn into
a red giant.
So excellent.
Yeah,
well, I'm glad we'll be around to see that. We've been speaking with Josh Caldwell. He's a Pegasus professor and associate dean at the College of Science at the University of Central Florida. He's also the co-host of the Walkabout the Galaxy podcast. Josh, thanks for scaring the crap out of us.
Always my pleasure, Brendan.
Still to come, the telltale heart of a black hole.
But so far, we know of a fairly large number of black holes, and only recently there was a press release where some astronomers using an X-ray satellite confirmed that a second black hole really does, in fact, have the same kind of heartbeat phenomenon.
That's ahead on Are We There Yet? On this spooky Halloween episode. What's the scariest thing about space? If you're a listener of the show, you probably know my answer. It's black holes. After a star implodes, a massive black hole is created that has such a strong gravitational pull, not even light can escape it. But even though it sucks anything in its path and is in total darkness, it does have a heart. Well, not the kind of heart that we think of. Some supermassive black holes have a pattern of energy and plasma that flings out into space and mimics the thump-thump of a human heartbeat. Here to talk more about black holes and this eerie beat is Stephen Eikenberry. He's a professor of optics and photonics and physics at the University of Central Florida. Stephen, welcome to the show.
Thank you very much.
Well, Stephen, we had you on the show to talk about heartbeats of black holes, but I think we have to take a step back. First of all, how do scientists and physicists like yourself find black holes in the first place?
So the way we find black holes really starts with the birth of X-ray astronomy. X-rays are, as we all know from like medical tests and so on, are highly penetrating, highly energetic light particles, photons. And they are generated in extreme environments. We can do that here on Earth through a variety of mechanisms, but also out in space. The way that can happen is if you have extremely high temperatures. We're talking like tens of millions or hundreds of millions of degrees. If you heat material up to that level, it will actually glow in X-rays. Not much gets that hot. So stars like the sun, they give out a little bit of X-rays in their corona where temperatures do get to be millions of degrees. But by and large, normal stars are pretty faint in X-rays. So when we built the first X-ray satellites, we looked out into space and saw little points of X-ray light, which everybody was surprised about. They didn't expect to see anything that extreme. It turns out that the conditions around black holes, where there's, we're talking about the most incredibly dense, strong gravity fields in the universe, material falling into a black hole can get heated up to those temperatures and glow in X-rays. So that's really how we kind of pinpoint these things to start with.
That's actually quite terrifying.
Yes.
Things get that hot.
Yeah. Going near an active small stellar mass black hole like that, you will die in a terrible, horrible fashion by and large.
Okay. So you do not recommend, Stephen, is what you're saying?
Do not recommend, would not try it.
Okay. You said so, I mean, black holes have been theorized for decades, but it wasn't until these X-ray satellites went into space to find them. And it was kind of by accident? Is that what you're saying?
Yeah, pretty much. The first X-ray satellite mission that found one of these sources was actually trying to find the reflected X-rays from the sun bouncing off the moon. And the reason that would be kind of cool is it's hard for a satellite to point straight at the sun because it will do things like melt your telescope with the visible light. But you can look at the moon and you can see the scattered X-rays. And better yet, the scattered light would actually have some signatures of what the moon is made of, which, of course, when we're talking about the 60s during the Great Moon Race, that was of tremendous interest. What's the composition of different parts of the moon? But instead of seeing that, instead they saw, while their satellite was pointed in another direction, a great big point of X-ray light coming from the constellation Scorpius. So they named it Scorpius X1, for first X-ray source in Scorpius. And that turned out to be the first, what we call an X-ray binary. So they went out with a regular telescope, tried to look for a star there. They found one. It was kind of faint and wimpy. But then they realized that star must be, and they found multiple X-ray sources now in different places on the sky, like Cygnus X1. And in Cygnus, they found a great big star there. But those stars still don't give off the kind of X-rays or nearly the quantity of X-rays that you can see from Cygnus X1. I mean, we're talking factors of 1 million mismatch or more. But what they did see is that Cygnus X1, the star in that source, was wobbling back and forth like it was orbiting something, but it orbited something they couldn't see in visible light. And then we were able to put together it's orbiting the source of the black holes, which is much smaller. By measuring the force that was being exerted on that visible star, we could actually figure out how much the thing weighed. And that told us it was something like 10 times the mass of the sun. And the only other possibility for things that make X-rays that we know of really are neutron stars. And they don't get that big. They max out at about 2.5 or 3 times the mass of the sun. So that was the first time we really said that must be a black hole.
The idea of black holes before this discovery, these supermassive, really dense areas in space, was it understood that they would emit such hot X-rays, or was that kind of a surprise?
No. This is what we call a post-diction in physics, meaning we discovered it and then said, oh, well, that makes sense now that we know it's there. But yeah, there were not people going out. Like I said, the X-ray astronomers were going out to look at scattered X-rays from the moon or from the sun bouncing off the moon. So they had no idea that there were X-ray binaries until we found them.
Fascinating. And even more terrifying. If I was scared of black holes before, I am now. So let's talk about these heartbeats that black holes have. I mean, you've described how you can measure the mass and the density of these, measure the X-ray emissions from these black holes, but they also have a bit of a cosmic heartbeat. What is that all about?
Yeah, so when we say they have a heartbeat, what we're talking about is looking at the X-rays that come from these things. And you can look at the brightness of the X-rays versus time. And one source in particular that we've known about for a while now, the microquasar, it shoots out streams of material at nearly the speed of light from close to the black hole. And then there's also an accretion disk, material spiraling into the black hole that gives off the X-rays. And what we can tell when we look at that source is sometimes it looks like a human heart EKG. So that's why we call them heartbeats, is there's a little blip about once a second. It just goes blip, blip, blip. And it might be once a second, once every few seconds, something like that. But it's sort of a quasi-regular beating of some kind of signal coming from the black hole.
Interesting. And is this something that you can, quote unquote, listen to, kind of identify areas where there could possibly be black holes that haven't been discovered before?
Well, I think the thing is, if you see a lot of X-rays, you've already got a pretty good idea that it's a black hole.
Gotcha. And stay away.
Or a neutron star. But we haven't seen any neutron stars have this particular kind of heartbeat mode of pulsation. So that could be one way. But so far, we know of a fairly large number of black holes. And only recently, there was a press release where some astronomers using an X-ray satellite confirmed that a second black hole really does, in fact, have the same kind of heartbeat phenomenon going on to it.
And are these consistent heartbeats, or do these heartbeats diagnose what type of black hole it may be, the size of the black hole, or anything like that? Can it tell us more than just the fact that it exists?
That's what we're trying to figure out right now. What is it telling us? The thing we know is that these things are what we call in astronomy quasi-periodic oscillations, QPOs. But that's the same thing as basically saying an irregular heartbeat. And sometimes it can be fairly regular, just like your heartbeat. It goes up and it goes down. And so we can see the rates increase and decrease, but they're still more or less regular. Sometimes, though, it looks like a bad EKG, where your doctor gets really worried because you're skipping beats. Sometimes you go beat, 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 pause, beat, pause, beat. Weird kind of skipping and jumping happens. And what that is telling us, because we know the X-rays come from the closest region to the black hole right before the material spirals into the event horizon and disappears from the universe forever, we know that we're probing the material there. We know it's highly magnetized. One of my PhD students was one of the first people to show in the first heartbeat black hole about 20 years ago that we could actually see little puffs of infrared light coming out as well. And that's associated to these relativistic jets, these streams of highly magnetized plasma shooting out from the system. So we know those are tied to the heartbeats as well.
You mentioned these are quite rare, seen in only 2 out of hundreds of black holes. Is the thought that these heartbeats are a rare phenomenon, or is it just that you haven't heard them yet in other black holes?
I think a mix of both.
Okay.
So we haven't heard heartbeats from others, but you have to keep in mind, even though the 2 heart-beating black holes that we're looking at, they only do this when they're in the mood to do so.
Okay.
So sometimes it happens, and it can happen for days on end. Sometimes they'll go weeks or months without showing this heartbeat pattern. They'll show other kinds of variability, other kinds of flares and various jumps around in their brightness. But the heartbeat in particular, the one that looks just like an EKG, that comes and goes. And so there are almost certainly black holes that we're looking at now that might go into a heartbeat mode, but we haven't seen it yet, partly because they might not have done it. We've only been studying them for a few years, so maybe they don't do it that often. Also, we're not looking at them 24/7 with enough sensitivity to figure out whether they're producing heartbeats. We need more telescope facilities to do that. And then it just may be that some black holes don't do this. And in fact, the ones we do see the heartbeats coming from tend to be sort of these bigger black holes. And it depends on the state of the material that flows into them. And that depends on the companion star that they're, basically vampirically pulling matter away from them and sucking them into their own gravitational pull. So you have to have kind of the right circumstances in the X-ray binary. Then there are a whole nother kind of black holes that we call supermassive black holes that seem to be at the center of most galaxies, like our own Milky Way. So the ones I've been talking about are stellar mass. They may be a few times the mass of the sun, maybe 10, maybe 15 at the high end. Then there are these supermassive black holes where they are 5 million, 500 million, a billion times the mass of the sun. And some of those have also some signals that look reminiscent of the heartbeats, and people have claimed to see heartbeats from them. The trick with those is because they're so big, the time scale for them to do this changes from seconds to weeks or months. So it gets really hard then to study them long enough to see that happening. That's why I study the stellar mass black holes. I have too short of an attention span for the big ones.
I'd be right there with you. And Stephen, how you're describing them, if you have vampiric tendencies, these are literally things that go thump in the cosmic night. I mean, black holes are scary, they're destructive. Do they get a bad rap? What good comes out of black holes? Why do we even care that they're there?
Yeah, they are scary in the sense, the X-ray sky is pretty dark. And whenever you see a nice bright X-ray light, that usually means that there's a black hole or a neutron star literally eating its neighbor, right? It's pulling material off of its neighbors or off of, in a case of a supermassive black hole, a whole bunch. It can even eat entire stars in one gulp. So these are monsters out there that are definitely, sucking the life out of their neighbor stars and using that to survive and make the bright X-ray light we see. The good thing about them, first of all, is they're really far away. So we don't have to worry about one coming to eat us anytime soon. But also, in a more serious note, we can use them to study the most extreme conditions in the universe. And this becomes a real testing ground for us to probe the laws of physics as we know it. And so we're using them to try to check out Einstein's theory of general relativity in the most extreme cases that we can, where we're more likely to see if there are any flaws or exceptions to his physical description of the universe.
So there is some good to these very, very scary phenomenon in the cosmos.
Yes.
So thanks for being an advocate for black holes, Stephen. I appreciate it. We've been speaking with Stephen Eikenberry. He's a professor at UCF of optics and photonics, along with physics. Stephen, thank you so much for joining us.
Great. Thank you.
Well, that's enough spooks and frights for this year on this week's Halloween show. If you're not already, be sure to subscribe to the show's podcast feed so you never miss an episode. Do that on Apple Podcasts, Spotify, YouTube, or wherever you get your podcasts. Stay connected with this show. Be sure to follow us on social media. You can find us on Instagram and Facebook. We're at AWTY Space. And if you got an idea for a future episode of this show, you want to join us as a guest, or if you've got something spooky you want to share with us, email us. We're at arewethereyet@cfpublic.org. More space coverage on our website, cfpublic.org/space. This show, Are We There Yet?, is a production of Central Florida Public Media. Our producer is Marion Summerall. Our intern is Jenna Weiss. Editorial guidance from news director LaToya Dennis. Support for Are We There Yet comes from our listeners. Until next week, I'm Brendan Byrne. Happy Halloween, and thanks for listening to the things that go bump in the cosmic night.